So in 6.4, we get to the answer to the question, why did we care about rational expressions? Why are we learning how to work with them? Well, it's the same reason we learned how to factor in Chapter 5. It allows us to solve more equations. So now we can take a look at equations with rational expressions in them. And to some extent, I would say I kind of consider these almost easier than the stuff we just did in section 6.2. It's very similar, so you don't want to confuse the two, and I'll wrap that up at the end of the section. But when we're solving an equation with rational expressions, right, terms with polynomials in numerator denominator, then the approach we want to use, we do still definitely want to factor all the denominators immediately to see what factors make them up, to do two things: determine the domain of the equation, which we'll come back to here in a second, and find the LCD. Once we find the LCD, we'll do something a little different than we were doing last time, and that we'll actually clear fractions by multiplying by it and then solve the equations, but then we will be doing this checking if the solutions are in the domain, and we'll get to that as well. So to walk through this first example, the idea here, with these denominators, we know from past chapters, I think chapter 2, that with a denominator of a fraction, we're not allowed for that denominator to be a 0, right? We cannot divide by 0. So the idea of domain, I'm going to put this off to the side here, the idea of the domain here would be figure out what x's we can't have. Well, for starters, we would say 5x can't be 0. Well, just simply divide by 5 on both sides, and that shows us that x can't be 0. This is telling you 0 is not a solution to this equation. You're not allowed to have 0 as an answer, because if you plugged it in, it would cause that undefined situation of a 0 in the denominator. Now 45 we could ignore because nothing will make that 0. 3x is another situation where if I said 3x can't be 0 and you divide by 3, you get the same thing. So it's still the case that the domain is just x can't equal 0, right? We could say it's the set of all x such that x can equal 0. That's using that set builder notation you've seen other places in the semester. So with that, or we could even use interval notation and say it's everything up to 0 and then everything beyond 0. We've learned both those approaches to notating the domain of a function or a expression. So with that, now that we know what x can't be, let's figure out what x can be. Well, it mentions to factor the denominators, which these really aren't factorable at all. So the next question is then figuring out what that LCD is. And for this particular set of what we call monomials, just look at the number parts and then the variable parts. 5, 45, and 3 have a number part LCD of 45. Right? 5 goes into it, 3 goes into it. So that's our 45. And then we need that x involved too, so an LCD of x as well. So 45x is our LCD. Now, the big difference here between this problem and what we did in 6.2, we're not going to rewrite these fractions, right? I'm not going to go ahead and make 3 separate fractions with 45x under each of them. Instead, we're going to use our trick from clearing fractions in an equation by multiplying both sides, or in other words, multiplying every term by this LCD. So that's usually how I write it. I write it with the 45x in front of every single term. So 45x times that term, that fraction, 45x times that term equals 45x times that term. And then I go through and I see what reduces or what cancels. So we've got the x's canceling and 5 and 45 going to a 1 and a 9. So all that's left here is a 9 and a 6. So that's a 54. For my next term, we see the 45s cancel, left with the x and the 8, so that'll be an 8x. And then here, the x's cancel, and x and 45 go to a 1 and a 15. So 15 and 2 would give me a 30. So notice, after that one step, multiplying every term by the LCD, you no longer have fractions in the equation. And that turns it into something much simpler to solve. In fact, this is even a linear equation. I would just subtract 54 on over, get 24, divide by 8, get x equals -3 as a solution. But then we have to remember what we did at the beginning was we listed the values of x that we weren't allowed to have as answers You got to make sure that this answer is not one of those. Make sure your answer is in the domain. Well, the only thing we couldn't have was 0. This isn't 0, so we're fine. So -3 would be the solution to that equation. And just like always, you could take that -3 and plug it in and verify that. So don't forget you have that ability to check your solutions. All right, number 2. Starting off with that step of factoring if possible. Well, this set of terms has a 3 as a GCF, so I'll factor that out, leaving me 2x plus 1. That does not factor at all. That does not factor at all. So now, as I do off to the side here, checking my domain, just to point out, the only thing that involves an x that could be a 0 would be this factor 2x plus 1, which shows up a couple places. So that's really the only thing we have to say can't be 0. You don't have to do it twice. Obviously, it's the same thing. So subtracting 1, dividing by 2, we find that x cannot equal 1/2. So the set of all x's such that x is not -1/2, that's it. Or again, negative infinity up to -1/2, hop over it, and continue on. So those would be ways to represent our domain. So now, with that factored, we now want the LCD. So back to similar to last section, section 6.2, we need everything in here that shows up in any of these denominators. Well, that 3 shows up there and also there. That 2x plus 1 shows up there and also there. And notice that's all it takes for each of those denominators to fit into our LCD. We can find all that. We can find the 3. We can find the 2x plus 1. So that's the LCD. So now again, I'm going to take that LCD times every single term. Now this does take some time to write out, but I suggest it because it allows you to see what happens. Also, I want to point out that I'm going to write this denominator in its factored form. Right there. I'm not going to write 6x plus 3. We factored it for a reason. So then minus the, I messed that up. I'm going to put my multiple first. So 3 and 2x plus 1 times me 1/3 equals 3 times 2x plus 1 times 2 over 2x plus 1. And so we get the 3's and 2x plus 1's to cancel, leaving us just 7. Minus, now here the 3's cancel, so it's 2x plus the 1 left over times a 1. Well, that's just 2x plus 1, but always be careful around minus signs, right? This is still in parentheses there. You're subtracting whatever your result was from that multiplication. And then here those cancel, and 3 times 2 is 6. So now I can very easily distribute that minus sign, combine a couple like terms, subtract the 6. This is just a nice linear equation here. Divide by 2 and get x equals 0. Now, this is our solution we're getting. Just go back and check your domain. The only domain issue was a -1/2. So this is perfectly fine. So 0 is our solution set for the problem. All right, next one. Doesn't factor, doesn't factor. We can break that down with an easy case. Numbers that multiply to +4 and add to -1, or -5, are -4, -1. So with that, if we look for our LCD, notice we've got a factor of t minus 4 and a factor of t minus 1, so that makes up our LCD. Oops. Also notice if we come over here and ask about the domain, we've got that factor there and that factor there, and those are the only issues, it looks like. So t minus 4 can't be 0, t minus 1 can't be 0, so it can't be a 4 or a 1. So again, in solution, or in set builder notation, we would say t can't equal, usually they write it something like that, 1 or 4. Interval notation, a little trickier because we got to say up to 1, hop over 1, but then get to 4, hop over 4, and go off to infinity. So now, with that being said, and with that as our LCD, we come down here where there's room and write this t minus 4 times t minus 1 in front of each of these terms. So So there, then the t minus 4, t minus 1 in front of the 3 over t minus 1 equals t minus 4, t minus 1 in front of the t plus 11. And then again, writing that in factored form. All right, so again, I know it takes a lot to write out, but it's worth it to see exactly what cancels and what's left and not lose any signs especially. So t minus 4's cancel. So I've got a 5 times t minus 1 left there. T minus 1's cancel. I've got a minus and a 3 times t minus 4 left there. Here, both cancel. Left with the t plus 11. All right, so continuing from there, we can do some distributing of the 5. Here you can call that distributing a minus or a negative 3. So negative 3t plus 12. Combine some like terms over here, get 2t plus 7. Now, again, it's just linear, so I'll move all the terms over to one side, subtract the t and subtract the t and subtract the 7, rather, to get t equals 4. Now, in doing that, we're getting our answer of t equals 4, but if we come back up to our domain, because of one of our denominators, we said 4 was not an option, right? We're not allowed to have 4 as a solution. And if 4 is the only solution we just got, then we have no solutions, and thus we have a special case of no solution, or what's sometimes represented as the empty set, right? There's no answers, the empty set of solutions. So that's what we have to check for. We check our solutions against the domain, because if they were part of the domain issue, we remove them from the possibilities. Okay, and one more. Can't factor. That's a difference of squares. The factors to x plus 3, x minus 3. So it looks like our LCD is, again, just a combination of those two factors. That is, I'll say, a coincidence. It is just not always going to be this way. Always look at the factors that make up your denominators and figure out whatever combination is required there. But also for the domain, the only things that involve x are those two factors. So x plus 3 can't be 0, and x minus 3 can't be 0. So x can't equal negative 3, and x cannot equal positive 3. Back to our problem, we will simply multiply each fraction by that LCD. So x plus 3 times x minus 3 times that fraction. And the next one. And then on the other side of our equal sign, don't lose that negative sign, there is a negative 12 over x squared minus 9. Oops, I meant to write that as our factored form, x plus 3, x minus 3. So x minus 3's cancel. Left with an x times x plus 3. X plus 3's cancel. Left with a 2 times x minus 3. Here, the reason I want the factored form is they both cancel. Left with just a negative 12. So after you do that step, it should always be much simpler, right? No fractions at all. Now we just go to simplify and combine like terms. That'll be an x squared plus 3x plus 2x minus 6. I can even bring the 12 over if I want, plus 12. Because notice, I'm going to go ahead and decide I want this thing equal 0 as soon as I see this x squared pop up. This is not going to be a linear equation, so I will go ahead and move that term on over to be prepared for that. So x squared, combine the like terms there, 5x, like terms there, plus 6 equals 0. Now, this is a factoring of an easy case, right? GCF is 1, easy case. So we break that down. Numbers will multiply to 6 and add to 5, 2 and 3. So we've got two possible solutions of negative 2 and negative 3. 2 possible answers. However, looking back up at our domain issues, -3 is not allowed to be a solution, so we get rid of him, and our only remaining solution is the value of -2. And so the last thing to talk about, as I mentioned at the beginning of the section, is just to make sure whenever you're working these sections of 6.2 and 6.4 especially, to understand the difference in what you're looking at. I just wrote the problems because I wanted to focus on what the words would be. You see an equation here, right? This will have the directions of solve the equation. Here you see no equal sign. Back in 6.2, this is a problem, or something similar to a problem you'd see in 6.2, where it would say, it'd either say add or subtract, or simplify the expression. And so those are the words you want to make sure you understand the difference of, and when you see the problems, understand the difference. Here, the stuff we just learned, you're going to want to find the LCD, but then you're going to multiply every term by the LCD. That's our first set of steps there to get that in a simpler form. We do not do that over here. Don't go back to 6.2 and start multiplying by LCDs. Here, we find the LCD, and then we called rewrite equivalent fractions with the LCD. We find the LCD, and then we rewrite every single term as a fraction with that LCD in it, and then combine them through addition, subtraction. So just as a summary, comparing basically 6.2 to 6.4. That's something you want to definitely be aware of, especially when you get to things like the quiz and the test, identifying the directions and the problems. Really just boils down to if it's got an equal sign or not. If it's got an equal sign, we want to clear fractions. If it doesn't, we are stuck with them and we have to rewrite them and combine them.